All right, so SN 1987A, or that's the supernova that occurred in the year 1987. A was the first one that occurred that year. Was, as I said before, was in the large cloud of Magellan, which is a neighboring galaxy. It's I forget how far. It's like 150,000 parsecs, 150,000 light years or so. I can't remember exactly how far it is, but it's outside of our galaxy, and it exploded, and this was this was the closest one. I mean, there's supernovae going off all the time in other really distant galaxies, but this was very close to us. Basically like the town next door, if you will. And this happened during modern times, where we had sophisticated telescopes to measure the light curve. So if you look at this light curve is a little different than the Type 2 supernova that we normally talk about, and we think that this one shows all the characteristics of a Type 2 supernova, because there's a remnant, right? There's an actual material that is still there. So this is the debris that's going from this, and we can actually identify the what's remaining in this. Let's see, glowing visible, and see there's a small central object that's still there. All right, so this is what I was talking about before. So during a Type 2 supernova, and to some extent during a Type 1 supernova, but not to as much of a degree, and not these heavier elements. But anyhow, for Type 2 supernova, this is what the general percentage of the elements that we see. Of course, hydrogen and helium have been around since the beginning of the universe. That they were created during the Big Bang itself. But remember, it's stars that create the heavier elements, right? All the way up to uranium, which is the last element that's created in supernova. All right, so you get you go beyond helium, right? You got lithium, boron, beryllium. They are not as likely to occur or as to be created. You can see there's a much smaller percentage of those elements, and then you jump up to carbon, of course, right? And so that's because of this thing called the triple alpha process. Helium is available within stars, and it's available to fuse. If you notice what happens next, right? So you're gonna create, once you have carbon, again, think about it this way. There is this element which is helium, but it's really a helium nucleus, right? These stars are so hot that the helium has been stripped of its electrons, and that the helium nucleus, which is just 2 protons and 2 neutrons, stripped of its electrons, is also known as an alpha particle. That's a radioactive particle that we find, in radioactive decay. Anyhow, that has a lot to do with what elements are created, and the relative abundance of those elements. So if you can add basically an alpha particle to one of these elements, it'll create for example, carbon, right? Carbon is element 6. If you add a helium nucleus, which is also known as an alpha particle, to carbon, to fuse with carbon, then you're going to get oxygen, right? Notice the next element after carbon, of course, is nitrogen, but you're not going to get as much nitrogen as you're going to get oxygen, because the carbon and the helium will fuse in greater abundance, right? And so you're going to get more oxygen. So once you get carbon, you're going to get more oxygen than you're going to get nitrogen. You're going to get a good amount of nitrogen, but and the same thing goes. So then the next one would be what combines. So what combines with oxygen? When you have helium with oxygen, then you're producing neon, right? And then so you get this spike in neon and so forth, right? Each of these peaks right here, even though they're decreasing, they're going down. You're always taking the next heaviest element with helium, and so these are going in steps of 2, right? Right. So that's how you're getting this what's called the relative abundance, right? You get the carbon, and by the way, this is occurring to some extent in white dwarfs as well, in the ones that explode as white dwarfs, the type 1 supernova. You get some of this process occurring. Of course, in more massive stars, you're getting more of the process. I mean, just think of it that way. The more mass, the more of these elements that are produced. And now, the thing about iron is, the iron is over here. So remember, iron is the most stable of the atoms on the periodic table, because fusion will create iron, and then fission will also ultimately create iron. Let's look at what goes on with these peaks and these valleys. That's what the next stuff is about. And then of course how do you create elements heavier than iron? All right. So, as I was mentioning, of course, you got the triple alpha process to create carbon, right? So remember, there's always helium nuclei available, and they're fusing into carbon. So, but once you get the carbon, what happens is you're going to get the particle alpha process. In other words, you get an element like carbon. And carbon 12 is the most abundant, let's say there's 2 carbon 12s that come together. You're going to get magnesium 24, but not to the same extent that you're going to get oxygen, right? Because carbon 12 and helium, an alpha particle, which is also a helium nucleus, will form oxygen, right? Oxygen is element 8. Right, so you're going from element 6 to element 8. So it goes in steps of 2 more abundantly than it would go, in steps of 6, for example, where 2 carbons come together and create magnesium. All right, I mean these things are happening, but what's going to happen most frequently is whatever element is fused, and so you start with carbon. Then you're going to go up 2, and then whatever element that is, so that of course it was going to be oxygen, and then you go up 2, and so forth, right? You keep doing that, and that's called the alpha particle fusion process. All right, so remember we had triple alpha that created carbon, and then carbon plus an alpha particle creates another element, which in this case is oxygen, and then that oxygen with helium is going to produce, element number 10, and then 10 and an alpha particle is going to create element 12, and so forth, right? That's how you're getting. Oh, and no, this is the good example right here. Okay, so, this is actually further along. So you're getting a whole bunch of different particles. So like there's an alpha particle with silicon, right? And then that's going to create sulfur, and then sulfur and an alpha particle is going to create argon, and then argon and an alpha particle is going to create calcium. All right, do you see how that goes? You're getting all these produced by an alpha particle plus whatever element is fused, whatever element came before it that was fused with the alpha particle. All right, so these are basically steps of 2 because there's lots of alpha particles available. All right. All right. So the last nucleus in the in this alpha particle chain is, as it says, nickel 56, which decays. It's radioactive. It decays into cobalt and iron 56. Iron 56, of course, as we've mentioned before, is the most stable of the nuclei. So it doesn't fuse or it doesn't decay due to radioactive fusion. Let's see. Cores with the most massive stars, neutron capture can create. So this is you're talking about masses greater than, let's say, 8 solar masses. What's happening there is you get this iron, right? Iron 56, which is created, but then what's going to happen is you'll have free neutrons floating about, and the free neutrons will undergo nuclear reactions with the iron and then whatever else comes after, the heavier and heavier. It's creating heavier and heavier elements from iron all the way up to the last non-radioactive element, which is bismuth. In fact, bismuth only has one isotope. The isotopes are just the same element but different numbers of neutrons. Anyhow, bismuth 209 is the last element on the periodic table that is not radioactive. Right? Everything heavier than bismuth is automatically radioactive. It's just the way nature works. By adding or subtracting neutrons, that's basically what makes something radioactive. If you get some of these things are very, very stable, like iron, which of course is element 26, right? So it has 26 protons, and then take 56 minus 26. That's the number of neutrons it has, right? And so as you go up the periodic table, you need more and more neutrons to stabilize the atom if it's not going to be radioactive. And what I'm saying is, when the last one that is stable and it is bismuth 209. So you go any element above bismuth is naturally radioactive. All right. Let's see. So and then heavier elements, heavier than bismuth, which again you can go all the way from iron to bismuth without an explosion, just with neutron capture. You can create all the way up to bismuth. Now, elements heavier than bismuth, and bismuth is pretty far down the periodic table. I forget what element. I forget what the atomic number of bismuth is. I mean, you can look that up. But like thorium and uranium and things like that are heavier, and they're just naturally radioactive. So, but that stuff is created during a supernova explosion, and that, of course, we're talking about a type 2 supernova explosion. Okay, let's see. I guess. Well, I would have to look it up, but I'm pretty sure like a little bit of the heaviest elements were going to be created even during a type 1 supernova explosion, but not to the extent that they're created during a type 2. All right, so and then what we're seeing is like this is here's a curve that shows a type 1 supernova explosion, and then here's a theoretical curve, and they agree, the light curves agree with each other. So I mean, that's actually a pretty big deal when the theory of the light curve agrees with what we actually see in these explosions. Let's see. Now this is a big idea. This is one of the